Okay, so the next question that we have is question number 4. Basically, we did already question number 13. So let's go over to question number 14. So question number 14, we have defined a binary operation star on the set. Number 14, define a binary operation star on the set 0, 1, 2, 3, 4, and 5 as basically as A star B, as A star B is equal to A plus B, for basically if A plus B is less than 6, and then you have A plus B minus 6 if A plus B is greater than or equal to 6. So if A plus B is less than 6, then A star B is equal to A plus B, and if A plus B is greater than or equal to 6, then A star B is equal to A plus B minus 6. And the question that you want to answer here is show that 0 is the identity for this operation. Show that 0 is the identity for this operation, and each element A not equal to 0, and show that each element A not equal to 0 of the set is invertible with 6 minus A being the inverse of A. With 6 minus A being the inverse of A. That's basically two things that we want to show here, right? Okay, so now in order to show that basically 0 is the identity for this operation star, so what you need to do is that basically the identity is, as we discussed before, the identity is some element E belonging to the same set where the operation is defined, and if it exists, it's called the identity, and the condition for that is that A star E is equal to E star A is equal to A, right? So basically E belonging to, in this case, basically let's call this, for example, the set A. E belonging to A, if it exists, must fulfill the condition that basically E star A is equal to A star A star E is equal to A for all A belonging to A, right? So now if I take any element from this set, if I take any element from this set and write E star A, and we want to show that 0 is the identity for this operation. So we want to show that basically that E equal to 0 is the identity for the operation star, right? Which means that this condition must be fulfilled. So meaning that 0 star A must be equal to basically A star 0 must be equal to A. If I check this operation, or if I write 0 star A, that is equal to basically so wherever you go in this set, any element of this set that you pick, it's either 0 or 1 or 2 or 3 or 4 or 5, right? Which means that and this element over here is 0, right? So that means that the sum of those two elements is going to be less than 5, is going to be less than 6, because at most you can pick a 5, and 5 plus 0 is equal to 5, which is less than 6. So I can use this clause of the definition, which means that I can write I can assume that A star B in this particular case is equal to A plus B, right? So A star B is equal to A plus B, which means that 0 plus A, which is equal to A. And also you can say that this is supposed to be 0 star A star 0. And also if you check A star 0, that again is going to be equal to A plus 0, which is equal to A. And therefore you can say that 0 star A is equal to A star 0. A star 0 is equal to A, and therefore 0 is the identity for the operation star. So that is basically the first part of this question, which says that show that each element, this part over here that says that show that 0 is the identity for this operation. The second part of this question is basically we want to show that each element A not equal to 0 of the set is invertible with 6 minus A being the inverse of A. Now, if basically, so we want to show that every element A not equal to 0, of the set A. So let me write it, for example, this way. For every element A belonging to A and A not equal to 0, that what happens is that is invertible with such that A inverse is equal to 6 minus A, as we said over here, is equal to 6 minus A. 6 minus A, right? Now what that means is that basically, so we need to show that, so based on this definition that we had here, so here we said that given a binary operation star on a set A with the identity element E in A, and element A belonging to A is said to be invertible with respect to the operation star if there exists an element B in A, such that A star B is equal to B star A is equal to E, and then B is called the inverse of A, right? So we need to show that basically, so if I pick any element here, assuming that A is not equal to 0, we need to show that A star 6 minus A star 6 minus A is equal to 6 minus A star A is equal to the identity element. And the identity element here is 0, right? Now, if you want to calculate A star 6 minus A, so what is the difference of A and 6 minus A? So if I write basically, so here we are saying that basically both those two elements added together. Now, those two elements added together would be A plus 6 minus A, and that would be equal to 6, right? That would be equal to 6, which means that I have to use this part, this clause of the definition. So A plus B minus 6. So A star B is equal to A plus B minus 6. A plus B minus 6, right? So what that means is that now, if I write A star 6 minus A, that is going to be equal to A plus B minus 6, which is A plus 6 minus A minus 6, and these two all will be cancelled out. You'll be left with the 0. Also, if I calculate 6 minus A star A, that's going to give me again A plus B minus 6. So A plus B minus 6 is going to be, this is going to be A, so 6 minus A, and plus B, which is basically A, minus 6. Again, you can cancel these out and you'll get a 0. Which means that basically A star 6 minus A is equal to 6 minus A star A, which is equal to 0. Which means that every element, now there is a problem here. There is only the problem that A cannot be equal to 0, and I do not see why A cannot be equal to 0. I mean, why A cannot be invertible. If A is equal to 0, then of course if A is equal to 0, let's suppose that A is equal to 0. Let's see what happens. So then 0 star, for example, star 6 minus 0, right? That would be basically the same thing as A plus B minus 6. So that would be 0 plus 6 minus 0, minus 6. Well, I'm still getting a 0 here. I don't see why that cannot be 0. But there is basically another way of solving the same problem. We will try that as well. So for now, based on what we saw over here, we can see that every element A belonging to A is invertible. With A inverse is equal to 6 minus A. Now there is another, this was question number 14. Now there is another way that they have solved this problem, and let me show you that way as well. Maybe using that way we can see why A cannot be equal to 0. So the second part, which is basically about elements being invertible and so on and so forth, it says that an element A belonging to X, is invertible if there exists B belonging to X, such that A star B is equal to 0 is equal to B star A. Now here what they have assumed is that they have taken they have taken this set most probably as X, and this is some element belonging to X, some element belonging to that set. This is supposed to be the inverse of that element, and this is the identity element which we already found here to be 0. That's basically why they have written this statement. Okay, so I had to go back a little bit in the video because, well, I couldn't understand the logic that they have used here. So if I write this statement as A star B is equal to B star A is equal to the identity element, that means that B is the inverse of A, right? Based on this definition. Based on this definition here, we said that given a binary operation star on A with the identity element E in A, and element A belonging to A is said to be invertible with respect to the operation star if there exists an element B in A such that A star B is equal to B star A is equal to E, right? So therefore I can write A star B is equal to B star A is equal to 0, and if that is true, then that means that basically B is the inverse of A. Now, so that what that means is that, so now I can write basically the rule that we had for this, the definition of this operation, of this binary operation, was that A star B is equal to A plus B if basically A plus B is less than 6, and it is equal to A plus B minus 6 if A plus B is greater than or equal to 6, right? So now I can write basically if A plus B is less than 6, if A plus B is less than 6, this case over here, A star B becomes A plus B. A star B becomes A plus B is equal to 0 is equal to B star A becomes B plus A, right? And moreover, I can write if A plus B is greater than or equal to 6, then a star b becomes a plus b minus 6, a plus b minus 6, and basically b star a becomes b plus a minus 6 is equal to 0 is equal to b plus a minus 6. Now what this gives me is that a is equal to negative b. So what this means is that, so here we are saying that a plus b is equal to 0, which means that a is equal to negative b, a is equal to negative b, and a plus b minus 6 is equal to 0, which means that b is equal to, basically a plus negative, or 6 minus a, right? Now this is not possible because we do not have negative numbers in X. You see over here we do not have any negative numbers here, meaning that any a that we pick in this set, you cannot assume that basically a is equal to negative b, because we do not have negative numbers in here, and therefore you can say that. So here I can write but x is equal to 0, 1, 2, 3, 4, and 5, and a and b belong to x, and a and b belong to x, then a is not equal to negative b. That cannot exist, right? And therefore I have to take the second one, which is b is equal to 6 minus a, is the inverse of a, for all a belonging to x, hence the inverse of an element a belonging to x, a not equal to 0, is 6 minus a, that is a inverse is equal to 6 minus a. Now still we didn't understand why a cannot be equal to 0, and the logic that has been used here, I had to struggle a lot in order to understand the logic in the first place. But it was an interesting logic that they had used. But I still prefer my own logic here. It's much more, it's much simpler, and it gets you to the answer. So, but this is another way of doing the same thing. Anyway, okay. So now let's do question number 15. Let's do question number 15. So question number 15 is, let A be equal to the sets negative 1, 0, 1, 2. Negative 1, 0, 1, and 2. And B equal to negative 4, -2, 0 and 2, and f and g are functions from a to b. What this means is that basically f is a function from a to b, and g is a function from a to b, right? The functions defined by the definition of these functions are f of x is equal to x squared minus x for x belonging to a, and also g of x is equal to 2 times the absolute value of x minus 1/2 minus 1, x belonging to a. Now you want to know the answer. The question that we want to ask here is, are f and g equal? Right? Are f and g equal? Now, as just a piece of information, because we haven't had this before, is that the definition of as a definition we can say that basically two functions f and g, two functions f from a to b and g from a to b are called equal functions, if f of a is equal to g of a for all a belonging to a. All of these a's, of course, come from a, so meaning that the domain of both of these functions are a, and we are assuming that lowercase a is some member of this set a. And so basically two functions f from a to b and g from a to b are called equal functions if f of a is equal to g of a for every a belonging to a. So having that in mind, we want to answer this question, which is, are f and g equal functions or equal? Okay, so this question is, well, not that complicated. It's simple. Basically, you have these two functions f and g, and both the domain of both functions is a, the codomain of both of them is b, and then all you need to do is basically check whether the outputs of each of these functions f and g's are the same for each of the inputs, meaning that the way that I would write this would be basically so we have basically these two functions. Now if you calculate f of -1, if I calculate all of these, if I input all of these values into this function f, I have basically f of x is equal to x squared minus x, where x belongs to a. So if I calculate f of -1, for example, f of -1 is equal to 1 minus 1, which is equal to 0. F of 0 is going to be equal to 0 minus 0, which is equal to 0. F of, for example, 1 is going to be equal to 1 minus 1 is equal to 0. is equal to 0, right? Am I not making any mistakes? Negative 1, 0, 1, 2. So if a is equal to negative 1, 0, 1, and 2, so if let me do this again, I might have made a mistake here. So if I calculate f of negative 1, that is equal to negative 1 squared minus negative 1, which is plus 1. That was what I said. So negative 1 squared is 1, 1 plus 1 is equal to 2. F of, for example, 0 is going to give me 0 squared minus 0, which is equal to 0. F of 1 is going to give me 1 squared minus 1, which is equal to 1 minus 1, which is equal to 0. F of 2 is going to give me 2 squared minus 2, which is equal to 4 minus 2, which is equal to 2. That is all the outputs of the function f for these inputs. Now the function g was, we said that g of x is equal to 2 times the absolute value of x minus 1/2 minus 1, where x belongs to a. So now if I calculate, for example, g of negative 1, that's going to give me 2 times the absolute value of negative 1, negative 1/2 minus 1. Now, negative 1, negative 1/2 is negative, well, negative 1, negative 1/2 is the same thing as negative 2/2 minus 1/2 is equal to negative 3/2. Take the absolute value of that, becomes positive 3/2. 2 times positive 3/2 is equal to 3. 3 minus 1 is equal to 2. Then, which is, as you can see, which is equal to f of negative 1 here. So 2 and 2 here. Now g of 0 is equal to 2 times 0, basically 0 minus 1/2 minus 1. So this becomes basically positive 1/2 when it comes out of the absolute value function. 2 times 1/2 is equal to 1. 1 minus 1 is equal to 0, which is the same output here. Now if you calculate basically g of 1, that gives you basically 2 times the absolute value of 1 minus 1/2 minus 1, which is equal to, now 1 minus 1/2 is equal to 1/2, so 2 times 1/2 is equal to 1, and 1 minus 1 is equal to 0, the same output here, g of 1. And g of 2 is the same thing as 2 times the absolute value of 2 minus 1/2 minus 1. 2 minus 1/2 is equal to 1 and 1.5, which is basically 2 minus 1/2 is the same thing as, well, 1.5, which is the same thing as 3/2, right? So 2 times 3/2 is equal to 3, and 3 minus 1 is equal to 2, the same output here. So as you can see, the outputs. So therefore, you can say that mathematically, we can say that basically f of a is equal to g of a for all a belonging to a, and hence the functions are equal. Hence the functions are equal, meaning that the functions f and g, of course. Okay, so that was question number that was question number 15. Now the next question that we have is question number 16, which is let A be equal to 1, 2, 3. Let A be equal to the set 1, 2, and 3. And then number of relations containing 1, 2, and 1, 3, which are reflexive and symmetric but not transitive. So then the number of relations containing 1, 2, containing 1, 2, and 1, 3, and 1, 3, which are reflexive and symmetric, symmetric, but not transitive, is choice A is basically 1, choice B is 2, choice C is 3, and choice D is 4. So this question does need a little bit of work. You need to, but it's actually pretty interesting, meaning that you get to work with all of those ordered pairs. Okay, so about this question. Okay, so basically I did solve this question once, but it seems that I did make a mistake. And so let's do the question one more time. And this is actually, it seems that this is not the right answer. Okay, so basically when you have basically a set A, which is basically 1, 2, 3, and then the number of relations containing, you have the number of relations on this set. So when we are talking about the number of relations on a set, that means that we have calculated the Cartesian product of this set with itself, meaning that I need to calculate the Cartesian product of A and A, which is all of these ordered pairs as, for example, 1, 1, and 1, 2, and 1, 3, and 2, 1, and 2, 1, and 2, 2, and meaning that basically you have the set A 1, 2, 3 over here. This is the set A, and then again you have the same set A here, and this is the set A. So you have all of these relations. One is related to 2, and then you have 2 to 1, 2 to 2, 2 to 3, and then you have basically 3 to 1, 3 to 2, and 3 to 3, right? And that is basically all that, basically 1 to 1, 1 to 2, 1 to 3, 2 to 1, 2 to 2, 2 to 3, 3 to 1, 3 to 2, 3 to 3. And that gives me 3 times 3, 9 ordered pairs. So I have 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and we have 3, 3, and that is basically that is basically the Cartesian product of A and A. Now, any relation that you define on this set A is a subset of this Cartesian product of A and A, meaning that a subset, meaning that it could be the set itself, the whole set, or some subset of the set based on some rule. And for example, the rule that we have right now in this particular case is that basically 1, 2, and 1 comma 3 must belong to that relation. It must be reflexive, it must be symmetric, but it must be not transitive, right? So what I need to do is that I define a relation, for example, R1 on this set, and I know that I need 1 comma 2 and 1 comma 3. Those must be there. 1 comma 2 and 1 comma 3. Moreover, I know that it has to be reflexive and symmetric. So reflexive means that we say that for the condition for being reflexive is that we say that for every A belonging to the set A, for example, the set that on which the relation is defined, we have A comma A must belong to R for every A belonging to A. That means that when I write my quantifier in the beginning here, in the beginning of the statement, what that means is that basically actually it's the other way around. It is the other way around. I wanted to talk about something about mathematical logic, but it is if A comma A belongs to R for every A belonging to A, right? So what that means is that you need to go into the set that you have, which is 1, 2, 3, and for each of those elements, A comma A has to be there. Meaning that, for example, since 1 belongs to the set A, then 1 comma 1 has to be here. Since 2 belongs to the set A, then 2 comma 2 has to be here. Since 3 belongs to the set A, then 3 comma 3 has to be here. And that means that now R1 is reflexive. Now for symmetric, basically the condition is that if A1 comma A2, if A1 comma A2 belonging to R implies that A2 comma A1 also belongs to R for every A1 and A2 belonging to A. And there is another, of course, condition for being transitive, which is if A1 comma A2, of course we are going to need it after this step, if A1 comma A2 belonging to R and A2 comma A3 belonging to R implies that A1 comma A3 also belongs to R for all A1, A2 and A3 belonging to A. These are the three conditions that we need to use in order to decide whether R is reflexive, symmetric, transitive, and so on and so forth. Now what that means is that now I have made sure that R contains basically these two elements that needed to be there, and it's also reflexive. Now we need to make it symmetric. So symmetric means that if A1 comma A2 belongs to R, that implies that A2 comma A1 belongs to R as well. Meaning that, for example, if 1 comma 2 belongs to R, that must imply that 2, 1 also belongs to R. So I have to put 2, 1 here as well. And if basically 1, 3 belongs to R, then that means that 3, 1 must belong to R as well. And 1, 1 is already symmetric, 2, 2 is already symmetric, and 3, 3 is already symmetric. So that takes care of this problem. And now this, we need to make sure, of course that is already the case, we don't need to worry about that, but we need to make sure that this relation is actually not transitive, right? So transitive means that if A1, A2 belongs to R and A2, A3 also belongs to R, meaning that, for example, suppose that you get something like 1, 2, as you can see, 1, 2 here belongs to R, and also 2, 2, as you can see, belongs to R as well. So I can take this number as A1, I can take this number as A2, I can take number as A2, and I can take this number as A3. So you can see that A2 and A2 are present here. That must imply that A1, A3, which is 1, 2, 1, 2 must belong to R as well. If that is the case, then you can say that R is transitive, otherwise not. Of course, only relative to these elements, otherwise there are other elements that you need to check as well, of course. So you need to go in and check for each and every one of those elements and see what is going on with the relation that you have. So I'm going to start, for example, with 1, 2. So 1, 2 ends with a 2, and the elements that start with a 2 are 2, 2 and 2, 1. 2, 2 and 2, 1. So this, if I take these two together, that implies that 1, 1 has also needs to belong to R1, so that R1 is transitive, which is already the case. And if I take these two together, that implies that 1, 2 must also belong to R1 as well, so that R1 is transitive, which is already the case. Of course, I do not actually want R1 to be transitive, but well, that's the way it is, and of course I cannot change it, because if I remove any of these elements, then the relation is either not reflexive, or it's not symmetric, or one of these is missing, which is basically, and that is also something that I do not want either, so I cannot touch that. Now, so the first element, we have no problem with it. The second element that we have is 1, 3. So now I need to go and check all the elements that start with a 3, which is basically these two, 3, 3 and 3, 1. So taking these two together, that implies that 1, 3 has to be there, which is already the case. And this implies that 1, 1 has to be there, which is already the case. So this element has no problem either, and so far we are transitive. We have, which is of course not necessarily a good thing. Now we have 1, 1 here, and then I have to go and start with all of the elements that start with a 1. So I have 1, 2, we have 1, 3, and that is that. So that implies that taking these two together, you get 1, 2 belongs to R, which is already the case, and 1, 3 belongs to R, which is already the case. So for this element you are transitive as well. Now the next element is 2 comma 2. Now I have to start with elements that start with a 2, and I have 2 comma 1. That implies that 2 comma 1 must also belong to R, which is of course already the case, so we have no problem there. So we have to go for 3 comma 3. So you have 3 comma 3, and all of the elements that start with the 3 is only this one, 3 comma 1, which implies that 3 comma 1 must also belong to R, which is already the case. So for this one you are also transitive. And then you have 2 comma 1. So this ends with a 1, so I have to start with all the elements that start with a 1. So I have 1, 2, and 3 elements here. So 1 comma 1, you have 1 comma 3, and you have 1 comma 2. So taking these two together, that implies that 2 comma 1 must belong to R. Taking these two together, that implies that 2 comma 3 must belong to R. And taking these two together implies that 2 comma 2 must belong to R. 2 comma 1 is already there. 2 comma 3 is not there. 2 comma 3 is not there. And 2 comma 2 is actually there. 2 comma 2 is actually there. So this one is missing. 2 comma 3 is missing, meaning that the relation as it is actually not transitive, because 2 comma 3 is not there, and therefore relative to this element, 2 comma 3 is missing, and so the relation becomes not transitive. And then checking the last element here, we have basically 3 comma 1. And so 3 comma 1 is basically starting with all the elements starting with 1. You have 1 comma 2, you have 1 comma 3, and you have 1 comma 1. So this implies that 3 comma 2 has to be there. This implies that 3 comma 3 has to be there. This implies that 3 comma 1 has to be there. So this is already the case because this is already there. This is already the case because this is there. And 3 comma 2 is not there. So relative to this, 3 comma 2 is missing. Which means that as it is the smallest relation that the smallest relation that you can find, which is reflexive and symmetric and contains these two elements here, is basically R1, and this fulfills all of our conditions, and it's also not transitive, right? So now there is something. Now the logic that I used the previous time, and that must have been faulty logic because it led me to a logical mistake, and probably because of that the answer was wrong, was that basically the way that I reasoned was that, okay, so since basically these two elements are missing, and basically these are the only elements that are remaining from this set, meaning that if you take a look at this relation, you have 1 comma 2, 1 comma 3, 1 comma 1, 2 comma 2, 3 comma 3, and then you have 2 comma 1, and then you have 3 comma 1. The only missing elements that we have not included here are these two, and these two are actually these two that are missing here. Meaning that now what I'm Now if you add any of these elements to this relation, suppose that I write, for example, R2, and I write 1 comma 2 and 1 comma 3 and 1 comma 1 and 2 comma 2 and 3 comma 3 and 2 comma 1 and 3 comma 1. Now suppose that I add this 2 comma 3 here. Suppose that I add 2 comma 3 here. This relation is still supposed to be not transitive, because this element is missing, right? Meaning that relative to this element, basically you have 3 comma 1, and then 3 comma 1 is basically you have 1 comma 1, 1 comma 3 and 1 comma 2, 1 comma 2 and 1 comma 3, and so that implies that 3 comma 1 has to be there. That implies that 3 comma 2 has to be there. That implies that 3 comma 3 has to be there. This is already the case. This is not the case. And this is already the case. 3 comma 1 is already there, right? So this relation is still not transitive, which is the logic that I'm using, and it's actually correct. But now let me actually check the answers in the book. So basically I do have a problem with this answer, meaning that I cannot logically accept the answer that is given here, meaning that you see over here, oh, okay, right, no, you see the answer is actually correct. See, what happens is that, so far we have all the way up to here. This relation is the same relation that we have here, and we have no problem with that. It contains basically these two elements here, and it is reflexive and symmetric, and it is not transitive, and we have no problem with that. Now as soon as I add this element over here, you see that the only two missing elements that I have here are 2 comma 3 and 3 comma 2, right? So when I add 2 comma 3, so of course one of the conditions that we had was that it had to be symmetric. So when I add 2 comma 3, then of course I have to add 3 comma 2 as well, so that the relation remains symmetric. And then if I add, meaning that suppose that I add 2 comma 3, then I have to add 3 comma 2 as well, and then I'll have added all of the elements, and then the relation becomes transitive, which is not what I want. So I can add actually neither of them, which means that this relation is actually not correct, and that is basically the only relation that you can find on this set, which basically satisfying all of these conditions, which means that the correct answer is actually A, right? So this is basically question number 16. Question number 16. Okay. Now I'm going to end this video here, and in the next video we will talk about the rest of these problems. I'll see you in the next video, and thank you.